Hey everyone, this is a video lesson that I'm using in my AP Calculus AP class, and I'm putting it online in case it would be helpful to others as well. This is the second video for this cluster, we'll call it, of sections on curve sketching. You can find a link to a printable set of guided notes that follow along with what I do in the video in the first video for this section. All right, in that first video, I talked for an entire hour about things like how to recognize when a function is increasing, when it's decreasing, when it's concave up, when it's concave down, and extrema, maxes and mins, and points of inflection. Yeah, we did a whole lot of stuff there. Where we are now is right here. Okay, we're going to do a few examples in this video where we put together things like the first derivative test, where we can test for extrema, with the concavity test, so we can test for concavity and points of inflection to figure out what the graph of the function should look like, and then we'll sketch the curve. Okay, so I think one of the things that I mentioned when we went over example 1 that will be really important as we start example 2 is that you should always think about restrictions of your function before you do any sort of testing of the first or second derivative. Okay, restrictions are always key to note. And so in example 1, we didn't have any restrictions because we had a polynomial function. But in example 2, we have a rational function, and there are values of x that would make the denominator 0. And so we better note that right off the bat. Here are our restrictions. When we set the denominator equal to 0 and solve, we would get x equals -1 and 1, right? So x cannot equal -1 and x cannot equal 1. And going even further than that, we should probably note what type of discontinuities that makes for the graph of our function. And so the way that I do that with a rational function is I think about, can I remove any factors in the denominator that would then cancel anything to get rid of these restrictions? And the answer to that is definitely no, right? There's nothing in the numerator that's going to cancel with anything in the denominator. And so that means that these restrictions are most likely, they are vertical asymptotes. Speaking of asymptotes, something else that we should consider with rational functions especially is, do we have any horizontal asymptotes as well? Because that would be nice to know. So, you might not remember this, but I'm reminding you right now. If you take the limit as x approaches positive or negative infinity of the function, you will find your horizontal asymptotes, if there are any. And so I'm not going to spend too much time on this, but if I would make x bigger and bigger and bigger, like, filling in numbers like 10 for x, 100 for x, 1,000 for x, and so on, you would find that you would get closer and closer to 0. And the same would happen if you filled in numbers like -10, -100, -1,000. Because it's squared, you would still get numbers that are just closer and closer to 0. And so that means that there is a horizontal asymptote also at y equals 0. We should probably say here vertical asymptotes at x equals -1 and 1. And so you could, get those set if you think that that would be helpful. And I think I'd like to mention before we begin doing any of our derivative tests anyway, that I scaled this one a little bit differently. I made this first sort of larger marking on the x-axis over here, -1, and this one 1. And yeah, I did the same thing with the y-axis as well. Okay, so we have vertical asymptotes at x equals -1. Try to keep that straight. It's not, but whatever. Then there's 1 at 1. There is also a horizontal asymptote at y equals 0, which is just right along the x-axis, which means I have a guide to keeping it straight, and I still can't do it. There we go. All right, so setting your asymptotes is good to do at the start. Now we get into the fun. Let's take a first derivative. And just a little reminder before we do that, a first derivative helps us because we can set it equal to 0 to get critical points. We can test those critical points to see if any of them are maximums or minimums. And then the signs that we get along the way in our testing will also tell us the direction of our function's graph, when it's increasing and when it's decreasing. Okay, so all good stuff there. Now, to do the derivative here, you could take x squared minus 1, raise it to the negative 1 power, and use chain rule. Or you could leave it in this form and do quotient rule. It doesn't matter, and I really actually don't think either one is better over the other. So I'm just going to stick with quotient rule, which remember is low d high. The derivative of 1 is 0. Minus high d low all over a low low. Denominator squared. Okay, let's clean that up a little bit. And in the numerator, we have a negative 2x. And in the denominator, we have quantity x squared minus 1 squared. Okay, so what we are going to do with this is we are going to find where it's equal to 0 or where it does not exist, because that is the definition of critical points. So as you work through the rest of the examples, this is where all of these boxes that we filled in, I'm trying to remember which one it was. Here it is. All of these boxes will come in handy because, you know, these are the places that it kind of guides you as to what you should do as you encounter each example. So if you need to know where your extrema are, where's your maxes and your mins, which, okay, I'm just telling you, you do if you're going to sketch the curve of the function. You want to know where its maxes and mins are. Then you're going to need to find critical points. And a critical point is defined as where the first derivative equals 0 or the first derivative does not exist. Now, I'll have more to say about where the first derivative does not exist in just a moment. But first, let's set the numerator of our first derivative equal to 0, because that's where our first derivative is actually equal to 0. Solving by dividing by negative 2, we get x equals 0, and that is one of our critical points. I'm just going to label it with a C. Try that again. CP for critical point. Okay, now, again, technically a critical point could also come from where a first derivative does not exist. And for this derivative, that would be setting the denominator equal to 0. Really, you could drop those parentheses with the power of 2 on the outside, because square rooting right away gets rid of that. And I hope you notice right away that what you're going to get out of this is what we got out of, you know, when we were thinking about our restrictions. You get x equals negative 1 and 1. However, do not label those as critical points. Okay, this is something that sometimes I can see students roll their eyes at. They're like, why do we even do that? Because sometimes they are not restrictions and they do end up being critical points. However, here they are restrictions, and so we're not going to label CPs there. We're going to just remind ourselves that that's where our vertical asymptotes are. So they can't be maxes or mins because they're asymptotes, okay? But still something that you need to consider. So now what we're ready to do is a y prime sign chart. And the purpose of this is to test our critical point to determine if it is a maximum or a minimum. But also, the signs on that sign chart will tell you where your function is increasing and where it's decreasing. So it really gets a lot of things set for your curve. Okay, so I'm going to definitely put my critical point here. But also, I would advise that you put your asymptotes so that you know that you can't use those values when you're testing for signs. And I even sometimes do this just to remind us that those are asymptotes right here. Okay, so at this point, we need to pick a number between negative 1 and 0 to test into the first derivative to see if it is positive or negative, you know, and that'll help us to determine if x equals 0 is a max or a min or neither. Okay, so I would think maybe we could go with like negative 0.5, right? That might not be so bad. And something that you need to keep in mind if you're not using a calculator to do this is that the denominator is squared. So whatever happens in here, it doesn't really matter because it's squared and is going to be positive, right? So really, I'm just filling negative 0.5 in right here. I'm thinking, okay, what happens when I take negative 2 times negative 0.5? I get a positive number. I don't care what number it is. I just care that it's positive, and that means that my function is increasing between -1 and 0. Okay, now let's do the same thing on the other side. This was x equals 1. That 1 kind of got lost in my dashes. It's x equals 1. We need to pick a number between 0 and 1. Let's go with positive 0.5. Fill it into the numerator because the denominator is squared, and you get a negative value. Okay, and that tells us that our function around x equals 0 is increasing until x equals 0, then decreasing, and that means that it is a maximum point. Again, this is where something that you wrote earlier in the notes could come in handy. There was a place where we wrote all of these tests. I think this is the one. Yes, I remember my colors. Okay, the light blue was the first derivative test. And, you know, we wrote out all of these different scenarios to show what we could have here. When we have f prime or y prime, whatever it is, the first derivative going from plus to minus around a critical point, that means that that critical point is a maximum. If we have the opposite, the first derivative changes from negative to positive, from the left to the right of the critical point, that is a minimum. And if there's no change, that means that it is not a max or a min. All right, before we say that we're done with this first derivative test, however, I do think it would be helpful to also test some numbers on the, or test a number on the other side of each asymptote, because you want to know what the direction of your graph is on each side of the asymptote as well. Really, if you think about it, because there are 2 vertical asymptotes, this graph is split into 3 sections, and you want to know what's going on in every section. So I'm going to pick something like -2 to fill in for my first derivative for x, and again, I just need to think about the numerator, which means take it times a -2, and that is positive. And so now I know that over here my function is increasing to this asymptote. And on the other side, something like 2 plugged into y prime would tell me that my function is decreasing because -2 times 2 is negative. Okay, so now I kind of have an idea. My graph is going up, then down, going down. Okay. So where should I put this? Maybe over here. Any really important points, you should get their y values, their function values, to plot them accurately. And so when x is 0, let's fill that back into the original function here to see what the y coordinate is. 0 squared minus 1 is -1. 1 divided by -1 is -1. And so now I know that I'm going to plot the point 0, -1, and it is going to be a maximum point. My graph is going up to that point, then going down. Okay, relative max, keep in mind. It's not the absolute max. We don't have a closed interval here, so we don't need to worry about whether it's absolute or not. It's not. All right. Before we sketch this curve, though, you could probably guess the concavity, first of all. I'm going to say that usually with these rational functions, at this point, you have a pretty good idea of what this graph is going to look like. It's going to go up, right? Go up, then down, and then go down. Okay, it's going to look something like that. But I will show you a concavity test for this function just so you can see what that looks like again. I will warn you, though, it looks a little bit crazy with a rational function, and again, it's not really necessary. In fact, I'm going to pause the video and put my second derivative up and bring it back to you just to make this video a little bit shorter, and then you can pause and copy it if you need to. Okay, here's my second derivative using quotient rule and chain rule right here. And now I can do this. We have a factor of x squared minus 1 here and here that can cancel with one of them down here. Okay, and then I'm going to clean this up and show you what that looks like. Okay, distributing the -2 through this set of parentheses and multiplying all this stuff together got me here, -2x squared plus 2 plus 8x squared, all divided by x squared minus 1 cubed. And then combining like terms, I'm now here. Y double prime is 6x squared plus 2, all divided by x squared minus 1 cubed. Now, why did I do all of that? Well, I did all of that because I'd like to use the concavity test to determine the concavity and determine if there are points of inflection. Reminder from something that we wrote before, points of inflection, they're here, is a point where the graph of the function has a tangent line and where the concavity changes. And how you find points of inflection is you find where the second derivative is equal to 0 or does not exist, and that second derivative has to change sign around that value. Okay, so to find where the second derivative equals 0 or does not exist, you can do what we did up here with our first derivative. We can set the numerator equal to 0 and solve to find where it equals 0. And we can set the denominator equal to 0 and solve to find where it does not exist. Okay, but here's some good news. When you set the numerator equal to 0, you're going to find that you can't solve that. You would be subtracting 2, dividing by 6. You would end up with x squared is equal to -1/3. And then you would be square rooting from there, ending up with an imaginary number. And we're not going to do that here. We don't have imaginary numbers that will be our points of inflection. So we just say that can't equal 0 and move on. When we set our denominator equal to 0, that's finding where our second derivative does not exist. However, we have already done that numerous times in different variations. What we're going to get out of that is, again, -1 and 1, and those are already set as our vertical asymptotes. Okay. Now, what you're actually going to find, though, is that if you put those vertical asymptotes on a y double prime sign chart, they're not technically points of inflection because they are not defined points on the graph. However, they will be the places where your concavity changes. So watch this. I have no possible points of inflection here because I didn't get anything out of this process except vertical asymptotes. But still, when I test values around these vertical asymptotes and I look at their signs in the second derivative, I will see some signs change. Okay. So you can pick anything to the left of -1, fill it into your y double prime here, and keep in mind that this time it's cubed, so you would need to think about, both numerator and denominator. I'm not going to take too much time on that, but I will say that any y double prime value to the left of x equals -1 is going to be positive. Anyone in here, think about like 0. 0 is an easy one to think about, is going to be negative, and then anything on the other side of x equals 1 is again going to be positive. And so that tells us that our function is concave up from -infinity to -1 and from 1 to infinity. And our function is concave down from -1 to 1. Okay, so you can kind of think a portion or a u, a portion of or a u for up, and down frown, or a portion of the frown for concave down. Okay, so putting all of that together, you sort of have an idea about what the graph looks like. The only other thing that might be a little bit troubling to you is, where do you start over here? You need to draw a curve that is what? Increasing and concave up. Okay, but what does that look like? Well, if you would look at the y values of any point in here, you will see that they're positive y values. And remember, there's this horizontal asymptote here at y equals 0. So you don't want to cross over that. And so the best bet is to do something like this. Increasing, okay, going along the asymptotes, concave up. Going along your asymptotes, increasing, concave up. It's going to mirror on the other side. It is decreasing on this side, but still concave up. Going along your asymptotes, it would look like this. And finally, in between -1 and 1, what did we have? We had a max at this point, 0, -1. So we are increasing to this point and then decreasing. And the concavity is concave down in there. So it's like an upside down parabola. Opening downward parabola, I should say. Like that. All right, now I know for that example, there was a lot going on here that might be a little bit confusing. So keep in mind that one of the main points of doing an example like this is just to talk about all of these different things that could occur with a function. You have your rational function. You have your restrictions. You have asymptotes, vertical and horizontal often. And then, your first derivative will give you your critical points and the direction of the graph. Your second derivative will give you possible points of inflection and the concavity of the graph. So it just sort of touches upon all of that stuff that you might need to know for curve sketching with a rational function. Okay. For example 3, we have another rational function, and it's a little bit trickier this time. The graph actually does not look as difficult, but it's a little bit trickier to understand what's going on here because we have a square root in our denominator, and that will affect our restrictions. Because I don't want to make this video too long, I am going to talk about the restriction mostly here and what that looks like. And then I'm going to mainly just put the other information out here, like the first derivative test and the concavity test, so you can see what it would look like. But I'm going to tell you right now, you're not going to be tested on something like this in my class, so I'm not going to spend too much time on it in this video. All right, let's talk about the restriction, though, because I think this is something that's important to understand. What we have here is an x is in a denominator, right? And we know that we can't have a 0 in the denominator. But also the x is under a square root. And so, we also can't have any negative values under that square root. So our restriction is a little bit more detailed than just setting it equal to 0. What we're going to do here is we are going to set the inside of the denominator, I should say. You don't really need that square root. We're going to set it greater than 0. Think about that. Does that make sense? You don't want it to be 0, so we can't say it should be equal to 0. We also don't want it to be negative, okay? And so we're basically saying here we want this x plus 5 to be something that's greater than 0 for, our values to work in our function. And this is a really easy solve. Subtract 5 on each side, and you get x has to be greater than -5. And that's actually the domain of the function. What we just found is the domain. We found what we're going to allow x to be. Okay, so what's that mean for our restriction? That means x can't be anything that is not greater than -5. So I didn't write it out here. I was like, what did I write here? I guess we could say x cannot be, anything. X cannot equal, we'll say, anything less than or equal to -5. Anything less than or equal to. Okay. And so what happens to the graph on the other side of -5? In this case, usually, is just nothing. There's just nothing there. Okay, so you sort of have a starting point here or a left end point at -5, but it is a hole. Okay, so I went back to scaling by ones with these little tick marks here. So this would be -5. And, you know, at some point here we have a hole. We can't sub -5 in to actually find a y coordinate. We could do a limit, but I would just suggest that you know, look at some other values, like -4 is going to be, what, 1? And, you know, so somewhere in here, there's a hole at x equals -5, and it's going to probably come down like that. Okay, I'll do the concavity and all of the other tests now to be certain of that, but that's sort of just a starting point from our information from our restriction. Okay, I'm back. I was working through this example. I'm like, this is just not my favorite. This is not my favorite at all. Okay. One of the things that I probably should have mentioned before I paused the video is that we do have a horizontal asymptote at y equals 0. So I thought about what happens when the limit is, what happens with the limit as x approaches infinity. Only positive infinity because we can't go in the other direction because of our restriction. And it does equal 0, which means that we have a horizontal asymptote at y equals 0, and that's probably one of our most helpful pieces of information. Okay, we're starting somewhere up here and we can't cross over that line. Okay, next I took a first derivative by rewriting the function as x plus 5 to the -1/2 power because it is a square root in the denominator. And that's why there's a -1/2 out in front here for our derivative. And, you know, from here it's power rule, chain rule, but the derivative of x plus 5 is 1. Okay, I rewrote that back into a fraction just to think about, oops, except that's supposed to be positive. Sorry. Just to think about, you know, what does this look like in this form to, you know, set my numerator equal to 0 to get critical points where the derivative is equal to 0, set the denominator equals 0. Okay, that can't happen here though. When I set the numerator equals 0, I get nothing because there's no x in the numerator. And when I think about the denominator equals 0, I get -5. That's a restriction. Remember, x has to be greater than -5, which means there's no critical points. Now, whenever you, you know, even though you don't have critical points, you can still do a first derivative sign chart test to think about the direction of the graph. However, your sign chart should look something like this, where you have an end point at -5, and you're just picking any number to the left of -5 to look at the sign of the first derivative. So any number you want that is not a restriction, you could sub in for x and see that your first derivative will end up being negative. Which means that your function is decreasing everywhere that it's defined, which would be from -5 to infinity. Okay, finally, going through a very similar process with y double prime to think about points of inflection. I end up with no possible points of inflection. I still, however, can do a little concavity test with a y double prime sign chart and pick any number that is allowed to sub into the second derivative, see that I get a positive value, and that means that my function is concave up over its entire interval where it's defined. And so what I'm going to draw is a graph that is decreasing, concave up, and not crossing over the horizontal asymptote of y equals 0. Just like that. That's it. That's all it is. Again, not my favorite, but there it is. Can we move on? Okay, let's go on to example 4. I like this one. Believe it or not, this one I think is fun. Okay, so we have a function y equals x minus 2 to the 2/3 power. And we don't have any restrictions this time, so that's kind of fun. No restrictions. That's supposed to be a star. I like to write it just to keep in mind that I did think about it. Okay, I did think about restrictions. I can't, oh my gosh, I just need to give up today. All right, there we go. which means we can just jump straight into our first derivative test to get possible, critical points, possible maxes and mins, and see the direction of the graph, and then move on to our concavity test. Okay, so for our first derivative test, we'll take the first derivative, and that is power rule. Like that, times 1, chain rule, don't really need that. And then let's rewrite it like this. And we can't set the numerator equal to 0, right? Because 2 cannot be 0. There's no x up here. But we can set the denominator equal to 0 to find a place where, I think this is interesting. Okay, this is our first example of a place where the first derivative does not exist, but it's not a restriction. Okay, let's set this equal to 0. Basically, let's just take the inside equal to 0 to save some time. And we would get x equals 2. Is a critical point. It's not an asymptote, it's not anything like that. It's a place where it is a discontinuity in the first derivative, because it's where the derivative does not exist, but it's not a discontinuity here. Okay, so let's throw x equals 2 on a y prime sign chart. That's the only point that you need to consider to be a point where the direction of the graph can change. And, how we're going to determine if it's a max or a min and the direction of the graph around it is by choosing a number to the left of x equals 2, like 1, and filling it into the first derivative to figure out the sign. Okay, so 1 would go in right here. 1 or 0 even. You would get a negative number no matter what you pick, right? And a negative number to the 1/3 power is still negative. Cube root of a negative is a negative. Multiplying by 3 doesn't change the fact that it's negative. And taking 2 divided by it doesn't change the fact that we have a negative value here. Negative. Okay, pick something to the other side of x equals 2, like 3. 3 minus 2 is 1. The 1/3 power is positive. It's all going to be positive. And so x equals 2 is a min. We know now that the function is decreasing to x equals 2, then increasing. Why don't we write that right now? Decreasing on the interval from -infinity to 2, increasing on the interval from 2 to infinity. So, maybe we should think about doing a little x-y table to see when x is 2, what is y? So we can plot that exact point. 2 minus 2 is 0. 0 to the 2/3 power is still 0. So we're going to plot our minimum point at, let's see, how did I scale this? I did this again. This is 1, 2, 3, and negatives over here. Okay, how did I know to do that? I just played around with it till it looked good. I did my graph a couple of times. We're going to do a point at 2, 0. All right, now, again, we know that the function is decreasing to this point, then increasing, but let's check how it should be curving as we do that. So our second derivative, let's go from here, is going to be -2/9 times x minus 2 to the -4/3 power. Okay, and lost an equal sign. We could rewrite that as -2 in the numerator, 9 times x minus 2 to the 4/3 power in the denominator. Okay, again, to find possible points of inflection, we could set the numerator equal to 0. That's not going to happen here. There's no x in the numerator. Set the denominator equal to 0, or it's inside, and what we get out of that is 2. Okay, but this is going to seem a little confusing, I think. It's not really a possible point of inflection. Okay, and here's why. if we go back to the definition of points of inflection, a point of inflection is a point where the graph of the function has a tangent line and where concavity changes. Okay, has a tangent line means the derivative exists at that point. Remember, we already established up here that x equals 2 was a place where the first derivative does not exist, right? So if the possible point of inflection isn't a point that actually has a tangent line, and how you would know that is whether it exists in the first derivative or not. So again, this point does not have a tangent line because it does not exist in the first derivative. You can cross it out. It is not a PPOI. Not a possible point of inflection. Now, if you didn't know that, you could still go through with your concavity test, which actually I'm going to suggest you do anyway. Okay, and you could still put, that double prime looks weird. You could still put x equals 2 on there, and it's not actually going to affect anything, but it's not a possible point of inflection. So I'm going to leave it off. Okay, the concavity doesn't change for this graph at all because I did not get a point of inflection at all in this process. And so I just need to pick any number I want, fill it into the second derivative, see the sign, and that's going to tell me the concavity everywhere for this graph. Okay, so I'm going to pick 0 because 0 is easy. 0 minus 2 is a negative number. However, I'm raising that negative number to the 4/3 power, right? So an even numerator here would indicate that that's going to change to a positive. Multiplying by 9 keeps it positive, so everything in the denominator is positive. Taking -2 divided by a positive number will then make your value of the second derivative negative. Okay, so the second derivative is negative throughout, which means our graph is concave down throughout. Okay, so this is where we need to be able to draw a graph that is decreasing to this point, then increasing, but it's concave down the frown the whole time. That's your cusp. That's your seagull. Whatever you want to call it. There it is. Now, we could pick some other points to try to make a better graph, a more accurate graph. But honestly, again, I'm going to move on because I'm going to try to keep this video not an hour long. So there you have it. Decreasing to our minimum, increasing on the other side, concave down throughout, very poorly drawn, but there it is, and it reviews everything you need to know. Let's review everything you need to know one more time, this time with a fun exponential function. Okay. Again, we're going to finish here with a function that has no restrictions. Yay. There's no restrictions on the domain of e, or e to the 2x plus 1. Okay, and let's see. There's something else that I want to mention here, okay? E is a number, right? Like 2.71828. And you're raising it to a power, raising a positive number to a power, and that's always going to result in a positive value. Think about like, okay, E is approximately 3 or 2, whatever you want to say. When you take that number even to a negative power, like to the -1, it just takes its reciprocal, right? -2 just takes its squared reciprocal, and so on. It's always positive. It's always positive. Even negative numbers in for x will result in a positive value. Adding 1, then for sure, is going to stay positive. So I think it's important to note here that you have only positive values for y. Okay, so you're not going to go down in here. All right, now let's do a first derivative. I like the derivative of e. It's easy, right? The derivative of e to the 2x is e to the 2x times 2, or I will write that as 2e to the 2x. Plus 1 goes to 0. Now, what do we do from here? We set this equal to 0 and solve to get critical points. But what's going to happen, you can divide both sides by the 2, is that you end up with an equation that you can't solve. You cannot solve this. Remember, we just said that this has to be a positive value. There's no number that you're going to be able to fill in for x that will even make this 0. Okay? No negatives and no 0. And so that means we have no critical points. But we can still do a y prime sign chart. We just don't put anything on it. We pick any number we want, like 0 in for x, like 1, 2, whatever, -1. It doesn't matter. It's always going to be positive, right? Because here's our first derivative, and it always has a positive value. And that means our function is increasing throughout. Now let's go through that process with our second derivative. It's going to look really similar, right? The second derivative is 2 times e to the 2x times 2, or 4e to the 2x. We could try to find possible points of inflection by setting it equal to 0, but we're going to end up with the same thing. It can't happen, so there are no possible points of inflection. Okay, so again, when we do our sign chart, we don't have anything to put on it, but we can still think about any number we want in the second derivative, and once again, it's going to be positive. Yay! Which means our function is concave up throughout. Okay, so the one struggle with this, I just paused the video to write this out, plus there was an announcement. The one struggle with this is, what do you do with all this information? You need to draw a graph that's increasing throughout, concave up throughout, right? But exactly what else can you do to sort of make it look good? Well, if you know anything about exponential functions, you know that they grow really quickly, right? And so I wrote out here, the limit as x approaches infinity of this function is definitely equal to infinity, meaning as x gets bigger and bigger and bigger, this graph's just going to shoot up. I just made a mark on the graph. Okay, but the limit as x approaches negative infinity, if I make x more and more negative, what is going to happen to this e to the 2x term is that it's not going to be ever exactly 0, but it's going to get closer and closer to 0. Okay, think about it. It does become a very, very small number because your negative power has that reciprocal effect. You can say that this will get pretty close to 0, add 1 to something that's pretty close to 0, and you end up with a limit that is equal to 1. And so, we can say that sort of what we have here is a horizontal asymptote at y equals 1. Not really, sort of. It is. Horizontal asymptote at y equals 1. It's just not one that you're typically used to seeing, with our rational functions. Those are a little bit easier to spot. All right, finally, let's get one value. Like, what happens when I fill in 0 for x? Just because I like to plot 1 point at least. Okay, well, what happens here? 2 times 0 is 0. And e to the 0 is 1, right? Anything to the 0 power is 1. So what I get out of this is 1 plus 1, which is 2. And so I know that I can definitely plot a point at 0, 2. I went back to just like each of these tick marks being 1 for this one. Okay, and now I know that my graph is probably going to look something like this. Going up through this point, concave up, like that. Yay, sort of. Okay, so I hope this video helped you to at the least, understand what different types of functions graphs look like. Okay, that would be helpful. Also, I hope this video helped to remind you of how to find critical points and how to use your first derivative test to find where your function is increasing and decreasing and maxes and mins. Also, how to use your second derivative to find points of inflection and the concavity test to determine the concavity or the curving of your function. Bye.